Hi, Bobcats. In this video, we're going to look at an example calculation of the heat that's associated with heating curves and cooling curves. So in this example, we are asked, what is the enthalpy change during the process in which 100 grams of water at 50 degrees are cooled to ice at negative 30 degrees C? So this is going to involve several processes. So on this slide, what I'm going to do is sketch out our cooling curve, right? Because we were talking about cooling, not heating. So if we were to look at temperature versus heat removed, which again, I'd always think of as being time. We're just removing heat at a constant temperature, and so the longer time goes by, the more heat has been removed. So we're starting with water at 50 degrees C. Well, the melting point of water is 0 degrees C, the boiling point is 100, so at 50 degrees we are talking liquid water, and we're going to cool that liquid water. When we hit 0 degrees C, I probably should label this is 50 degrees. When we hit 0 degrees C, that water is going to freeze, and so we're going to hit a plateau. And then once every little bit of liquid is turned into ice, and we continue removing heat, the temperature is going to drop until we end up at negative 30 degrees. So we have we have three different regions. In the first region, it's liquid water cooling. For that, we're going to need that specific heat of liquid water, which is this 4.184 joules per gram per degree C. So that's the constant we're going to use for Q equals mc delta T right here. For this horizontal plateau, this is where we have freezing taking place, and so we're going to need the delta H of fusion, which is the 6.01 kilojoules per mole. Notice units are all over the place here. The heat of fusion is given in terms of kilojoules, the specific heat's in terms of grams. The fusion is per mole, and the specific heat is per gram. And then last but not least, we have the solid cooling off, which means we need the heat capacity of ice, which is the 2.03 joules per gram per degree C. On these sloped portions, we're going to need Q is equal to the mass, because the heat constant is given per gram, then times the constant, then times the delta T. For freezing, we're going to have Q is equal to the delta H of fusion multiplied by the number of moles that we have, because the delta H of fusion is given per mole. So we're going to have to do three separate calculations and then add up the results of those three calculations. There is nowhere near enough room for me to answer it on this slide, so we're going to move on to the next slide. All right, so I've got a little bit more room to work with here. Just to remind us about what we're doing, I am going to sketch out this diagram here really quickly, because I find it's really, really helpful to always know where we are in terms of these diagrams. So that was negative 30 for the coldest temperature. It was 0 when it freezes, and then we're starting at 50. Okay, so I'm going to label this A, B, and C. Okay, in region A, we are going to have the liquid water cooling. And so the Q will be equal to mc delta T. So the mass of our sample is 100 grams. C, the specific heat for liquid water, is 4.184 joules per gram per degree C, and our delta T is 50 minus 0, because in this region we are going from, and that's delta or degree C. In this region we are cooling it. Now, deltas really should be final minus initial, but when I work these heat problems, I always set them up to give me positive numbers. And when I'm all done with the whole calculation, I ask myself, should this be endothermic or should this be exothermic, in order to make sure that I get the correct sign. And then I just assign it the sign that is the correct one for the process. Okay, so running this in my calculator, I've got 100 times 4.184 times 50, and that's giving me kind of a big number. Let's see, grams are going to cancel out with grams, degrees C cancel out with degrees C, and so the only unit left is joules, so I have 20,920 joules, and I'm just going to go ahead and convert that to kilojoules, 20.92 kilojoules. That's the energy that has to be removed from our sample to cool the 50-degree water down to 0 degrees C. Now, once that's at 0 degrees C, we need to calculate how much energy has to be removed to make the sample freeze. And then Q will be equal to delta H of fusion multiplied by how much stuff we have. And in this case, since the delta H of fusion is given per mole, we need to multiply it by the moles of water that we have. So our delta H of fusion is given as 6.01 kilojoules per mole. And then the moles of our sample, well, we know that we've got 100 grams, so let's do that conversion here real quick to turn that into moles. If I have 100 grams of water, to convert that to moles, I'll put the molar mass down in the bottom, which is 18.02 grams for every 1 mole of water. And so 100 divided by 18.02 is going to give me 5.55 moles. All right, so we'll multiply this down here by 5.55 moles. The moles cancel out, leaving me just kilojoules. So I'm going to multiply 5.55 times 6.01, and that gives me 33.35 kilojoules. And then last but not least, we have segment C. This is where the ice is cooled from 0 degrees C down to -30 degrees C. Since temperature changes are involved, once again, we're using the calorimetry equation. Q is equal to mc delta T. The mass was 100 grams. The C for ice, now we have to use a different C value because ice and liquid water have different numbers. It's 2.03 joules per gram per degree C. And then our delta T is from 0 to -30, so that's a difference of 30 degrees C. Degrees C cancel with degrees C, grams cancel with grams, leaving me just joules for the unit. So I'm going to take 100 times 2.03 times 30, and that's giving me 6,090 joules, or if we convert that to kilojoules, that'll be 6.09 kilojoules. Now to get the enthalpy change for this entire process, we've got to add up all 3 of these enthalpy changes. So boy, I am running out of room. So to help make this a little more organized, I'm going to change color. And so now we're looking at our total delta H. That's going to be equal to Q from step A plus the Q from step B plus the Q from step C. And so from step A, we had 20.92. From step B, we had 33.35. And from step 3, we had 6.09. And that's all in terms of kilojoules. So let's see, if I run that through my calculator now. Let's see, I've got 6.09 already showing, so I'll add these backwards. So plus 33.35 plus 20.92, and that gives me a grand total of 60.36 kilojoules for the total number for our enthalpy change. But now let's check and see that we have the sign of this correct. Okay, if energy is released from the sample, if it's given off, that's an exothermic process and we should end up with a negative sign. If energy is put into the system to make the process happen, then that's endothermic and we should have a positive sign. Well, in this case, we are removing heat from the sample as we're cooling it. Since we're removing heat, this is exothermic, and this should have a negative sign. This should be negative 60.36 kilojoules. We also know that because liquid is at a higher enthalpy level than a solid is, so even just that phase transition has to be exothermic, and the cooling is exothermic as well. Here are a couple of hints for working homework problems or quiz problems or test problems. Anytime we're talking about the calculations that go with one of these heating curves or cooling curves, draw the curve. It helps so much to be able to look at the curve and figure out the different calculations that you have to do and what all it is that you have to add together. So I'm a huge believer in drawing the curve on these problems. Now my second hint comes from a little bit trickier kind of problem. This is a calorimetry type problem back from Gen Chem 1, but those calorimetry problems didn't typically involve phase transitions, so that's the added wrinkle here. But the idea behind this is that the heat lost by the hot object has to equal the heat gained by the cold object. And I always, again, talk about these in terms of absolute values. I just make them all positive numbers. The amount of heat that is lost by the hot object has to be equal to the amount of heat that's gained by the cold object. And I think I totally skipped over the context here. So that the context on this type of problem is something like you put ice cubes into water and you're trying to figure out what the final temperature would be. So the heat that is lost by the water as it cools off is equal to the heat gained by the ice cubes as they warm up and possibly melt. You'll see this in calorimetry situations where like a hot object gets dropped into water and the heat lost by the hot object has to equal the heat gained by the water. And it's just so much simpler on the signs just to treat all of these heat processes as absolute values and then in the end figure out what sign should go with any of them.